Welcome everyone to the Lightning Talk session. Please welcome Stefano on stage with this Lightning Talk.
Hello everyone, my name is Stefano Fiorentino and this is an hit and run from header only to static linking library development. C++ header only library is enabling more and more library users to include dependencies in their project with ease. You just git clone or even copy and paste, and you can start work. The main drawbacks are executable size will bloat most of the time, and compilation time increase. When compilation takes long time, a little modification in the user space code yields a long compilation time or longer compilation time of the artifact. Maybe mainly due to the instantiation of your header-only lib. So your clients may accuse your library to slow down the compilation time of their project. Paying the cost of a little extra effort, you can transform your header-only library in a static linking one. Let's see how we can achieve this goal. Let's start from what this presentation is not about. If your header-only lib is only about variadic template aiming to manage Lambda function, this talk is not for you, will not help you, okay? What we are addressing. If your use of templates is about generic programming to allow several but limited configurations to work with the same library space code, and these configurations are completely instantiable with zero knowledge of the user space code, this talk, suits you, is for you. Let's see some code. Here is the main.cpp file, the user space code, the application code. You just want to include the header-only lib, and you want to use the namespace network that's inside the lib. And you may use bind with both configurations, IPv4 and IPv6. The header-only version of lib.hpp looks like this. You have a namespace network, inside this a subnamespace flags with a couple of configurations. And you have your template function. This template is declared and defined in the header file, hpp, and it's declared inline to avoid duplicates in your at linking time. The static lib version is splitted in .h and .cpp file. The network namespace is as before, with the namespace flags as before. But the template is only declared here, is not defined. And also, the external template declarations tells the compiler that the template will be instantiated elsewhere. Is not this the place where you want to instantiate them? Note the external keyword will be elsewhere, not here. The CPP looks like this. Include the lib, header, and the namespace network. Inside the namespace network, you have the definition of your lib. Functions, void bind, accept, NEP, and the port. And also, in the CPP file, you want to instantiate both configuration with network flags IPv4 and IPv6. Not missing both keywords missing. The inline one, because you want these to be instantiated in the CPP and maybe to be in the static lib only, and the external keyword. So this translation unit is the the one you want the instantiation of the template is in. You can provide so your client with a static lib with all configurations, or maybe some. Maybe you want to deliver a static library with only IPv4 and only IPv6 in 2 different artifacts, or none of them, and you will deliver the header-only library. Depending on the amount of library space explicitly instantiable code, you will have a lot of benefit from this technique. Let's see some number. This is an example from the UVW library, that it's a wrapper, a modern C++ wrapper of libuv. You configure the CMake step with UVW libs off. You build all the dependencies, and you build the tests. It takes 50 seconds almost. The second one is with the configuration of UVW libs on. So you have a UVW static and a UVW shard. In this case, we use the static one. Having built already the UVW static lib, the compilation of tests, so the compilation of the user space code, takes 16 seconds. So you have a 3-time speed up, or if you want, 70% less time in the compilation. Thanks for watching. It's less than 10 minutes, so
thank you. Will you be on Discord to eventually answer questions?
Yeah.
Take questions?
Yes.
Okay, so everyone, please feel free to join on Discord to ask Stefano any question. Okay.
Thank you.
Next up, thank you. Next up is Davide.
Hello, everyone.
Oh, okay. Please, the stage is.
So you will see that the title was slightly changed. The original title was Threads that join themselves. But I seriously hope that this case will remain a singularity. You don't really want to see threads joining themselves. First, let me start with the classic disclaimer. This is a presentation, so there may be typos in slides, and there may be toy examples. This presentation, the goal of this presentation is to simplify an idea with a somewhat reduced toy example. So please bear with me. I know the code. You will see buggy code, and you will be tempted to say, okay, in production, in our case, it will never happen. Let's see. So first, the motivation of all this. When you check the documentation for thread join, you will see what looks like a strange corner case, which is thread join can throw an exception marking that deadlock would occur. And this happens if the ID of a thread is the thread that runs join is the same ID of the thread that is being joined. And, you know, superficially, you may be tempted to say this is really a corner case. I mean, it really does take some effort to make it happen. So you need you need to notify the thread what's exactly its object in order to make it join itself. Looks like, you know, something that is very hard to happen in practice. So let's say our model is like something different. So we have a queue of jobs, and basically you call something like add the job, add the job, add the job, and there is a thread in the background that periodically checks the jobs that have been added and takes all of them and executes linearly. And then the public interface of the queue allows it to be stopped. So so basically the main function is super simple. There is something which is a sort of, say, potentially endless loop. While there are some more jobs, then add them to the queue and eventually stop the queue and wait for it to run everything. So here is like a very, very crude implementation. The constructor of the queue starts a thread, and the thread basically runs this sort of infinite loop in the background. So it kind of detaches the entire list of jobs and executes all of them. Very simple. The add another job is a sort of just a pushback, and the stop function is simply we notify the worker thread that it's time to exit, and we just wait for it to finish. Fantastic. Now someone asks to add a new feature. We want to exit the loop, not only when there is nothing else to be done, but when the user presses Ctrl+C. So what is Ctrl+C? Ctrl+C is a signal, and a signal is just simply an event that is delivered from outside to our process. And according to the documentation, basically we can simply register what is called a signal handler, which is a function that will be called automatically, passing the integer value of the signal. This is done very simply. We have to include a header. The signal handler is just a function, a C function with a simple prototype, and we call the signal API to register it. So what this code will do basically is whenever the user presses Ctrl+C, invoke the function exit gracefully, passing the integer value of cint. That was very simple. You can run it, and it may also work. But does it really work in every time? And reading the documentation more carefully, you will see that a signal is delivered to an arbitrary thread, which is basically ready. So what this means is that basically any thread can resume execution inside the signal handler as if it was a function call on the line which the thread is actually executing at the moment. So basically, we have a 50% chance that the worker thread actually is delivered the signal. So the worker thread itself will execute the signal handler. And because the Q is a global variable, it will try to stop it, which in turn will try to join itself. And this is our exception. So, well, it happened. Thanks for listening, and I will be on Discord, so if you have any question, feel free to ask me. Thanks again.
Thank you, Davide. And right now we have Noor.
Good morning.
Just a second that I have to share the slides.
So I can start saying I will introduce Utopia, which is a library. Okay. So
okay, the stage is yours.
Okay, thanks. So Utopia, it's a library, open source library that is developed by ICS, so the University of Lugano, Svizzera Italiana, Swiss, the Italian Switzerland, and CSCS, so the Swiss Supercomputing National Center. Could you please go on with the slide? Okay, thanks. So which is the motivation Utopia? So consider an engineering problem. Most of the cases you need to do a simulation. For example, in this case, I took a beautiful car and I did a simulation of the fluid pressure of the car. But in any time, you will end up with a linear problem. So A times X equal B, where you have this matrix and you simply want to invert this matrix. I would say simply, but it's not really simple. And the point is that you have this huge matrix. Often the matrix has billion of entries. So you want to solve invert in a parallel fashion. And thanks to the numerical method you're going to use, often it's finite elements or finite volumes, the matrix is sparse. So it means that most of the entries are zero. And when you want to invert the matrix, you want to keep these entries zero. Otherwise, you will not be able to solve the problem. So you want to avoid the so-called fill-in. To do this, right now, scientists are using mainly two libraries, which are PETSI and Trinos. Old-fashioned way was to develop a monolithic code writing from scratch, but it's not anymore scalable, not even feasible. So, can you go on with the slide? Thanks. So what are PETSI and Trinos? PETSI is the most used library. It's very easy to use. It's highly scalable. It's parallelized with MPI. So it's distributing the rows of the matrix on multiple nodes or multiple processors, depending on the hardware architecture. It's highly scalable. But unfortunately, it has a big drawback. Is not GPU based. It doesn't have any accelerator parallel code. And it's only based at the end on MPI. On the other hand, there is Trinos, which has more or less the same features, but in these years has been rewrote with a different idea in mind. Is the idea of using C++11 and focusing on performance portability. So the idea is to write one code that could run and almost to the native performance on different architecture. This thanks to Cocos. Cocos is an open source library developed still to Sandia Labs. They are trying to push to the standard C++ standard. And it's the key feature of Trinos. So what's Utopia? Utopia, it's a library. It's trying to glue together these two libraries. So please go on with the slide. Okay, so Cocos. Cocos gives you the possibility to abstract from the architecture, giving you some functionalities that are quite general among the different architectures. So it gives you some data structure with specialized memory spaces, memory layout, depending on the architecture you're going to use. Nowadays, the most stable and used are the backend for OpenMP and CUDA. And these backend are highly optimized by the vendor itself, are completely open source. And right now we have AMD that's been co-developed with AMD. There is CUDA that is co-developed with NVIDIA, and right now they are developing the version for 1MPI for Intel, for the Ponte Vecchio GPU compute cards. And give you also some parallel policies in order to perform the correct algorithm on different architecture. So please go on. Okay, why we are focusing on this? Because right now most of the scientists are using PETSI, and PETSI unfortunately cannot run on the modern, cannot run efficiently on the modern supercomputers. CSCS, here is CSCS, we have the most powerful supercomputer in Europe, one of the most powerful in the world. But unfortunately, it's mainly based on GPUs. So if you want to use efficiently our machine, you need to run on GPUs. And also for the future, you need to run code mainly on accelerators. And so our idea is to invest money to, modernize the code of scientists, but at the same time, not write, for example, in CUDA, because we are not sure if in the next 3 years we will still use CUDA or a different paradigm. So the idea is to try to have building blocks that can be easily recyclable. So please go on. Okay, so Utopia. Utopia is based on C++ 11. We can use also C++ 14. Unfortunately, we can use the latest version, the standard, because we are tied to CUDA, because CUDA has some bugs with C++ 14 and doesn't support 17 and so on. It's open source, it's BSD based. This is the link if you are interested. We have multiple backends. The most stable are PETSI and Trinos. So the focus is let the scientists still use PETSI in a classical way, but at the same time try to move on using Trinos to run on GPUs. So Utopia defined EDSL, and thanks to the EDSL, give the possibility to build on top of this EDSL the mathematical algorithm of the scientist. But at the same time, also it's quite easy to add new backends. So if you, for example, we are trying to now to add a new backend on Ginkgo library, and this gives also the user or other scientists to add other backends. Which are the features currently available in Utopia are mainly linear algebra and also nonlinear algebra. Please go on. Okay, so from the user application view, the idea is that you use the interface of Utopia, and at compile time, you can decide to use PETSI or Trinos, and therefore you can use CPUs or nodes with GPUs. And also, for example, GPUs means CUDA GPUs, but also AMD GPUs without changing the code. So the EDSL is with the DSL, you can build up an expression tree, then is evaluated by an evaluator. So it's quite a classical architecture from this point of view. Please go on. Can you go on with the slide? Sorry. Okay. So the idea, everything is based on the class tensor. And the Utopia primitives define the interaction between these tensors that generates an expression tree. This is easily evaluated, so it's evaluated only when it's assigned to another tensor object. Please go on. So snippet code. So the idea, you have this matrix object is actually a compile time. We define if it is a matrix from Trinos or PETSI. So at the end is the native object. And then we evaluate, so we adapt everything not with the expression, but when the expression is assigned to a matrix value. Go on. And we have here one example, the simplest example I can show you. It's the power method iteration. So you define matrix and vector, then you calculate matrix vector product, you calculate the norm, and then you renormalize the vector. And then you iterate until you reach the maximum number of iteration, or if you reach the convergence. So go on. So benefit of Utopia, it's hardware independent, and it's thanks to Cocos, but it's also software independent. It gives you the possibility to do not stick to a certain library, And often when a scientist or a developer is using this type of library, will stick tightly to one of these library. And this gives you the freedom to decide which one you want to use, because not always the algorithms which are implemented are always efficient. So you can switch between different algorithms between PETSI and Trilinos. It's perform portable thanks to Cocos. And it's extendable because, of course, you can add a backend, but especially if you want to use a specific algorithm that is not available in Utopia, you can build up with the interface of Utopia. So go on. So which are the features available? We have direct iterative solvers, so the big class of its solvers are both represented. We have preconditioners. Preconditioners are fundamental to stabilize the simulation or to speed up the simulation. We have both big class, so direct precondition and multi-grid precondition. And then we have nonlinear solver. We have two big set of functionality. One where they are one provided by the backend. So at the end, you are using directly the native implementation from a specific backend, or we have some new algorithms which are built on top of Utopia, so are using the data structure from the backend but are not using the algorithm of the backend. And this means mainly non-linear solvers like matrix-free method, multi-level method, or Hessian-free solvers. Last thing, you can even mix this advanced functionality solver of different backends. So go on. Application, I will show you some application. Go on. Application is currently used by two projects from PASC project, and which is the platform for advanced computing in Switzerland. One, it's a hemodynamic simulation. Here on the left, you can see a vein with the simulation. The blood is flowing inside, and there is simulating the shear stress on a valve that you can see right on the right. And then a completely different simulation. This is a geological simulation. It's a geothermal basin. So here we are simulating the injection of water into the faults underground, and we are extracting water for having a power plant, the power plants are in Tuscany. Maybe you heard about Lardarello. And the ellipses down are the activation, these faults. And the problem of these power plants is they are promoting earthquakes. And the simulation has been designed to try to forecast these earthquakes in order to minimize the risk of earthquake due to injection of water. So last slide. Summary, it's a library, open source library. There is a parallelized intranode parallelization in its MPI. Intranode is Cocos mainly. It's open source. We support PETS and Trilinos. It's very flexible for being used. It's C++11, and the future step are that we would like to add a general mesh handler, because currently PETS has its own mesh handler, but unfortunately Trilinos doesn't have. So we want to support Mars, which is another project we are developing, where we are handling, creating, and refining meshes on GPUs. It's based on Cocos, so it's hardware independent. And we would like also to add other languages bindings like Python and Fortran mainly because scientists are using mainly Fortran. And we are also investigating other algorithms like multi-precision algorithm and parallel time algorithm. That's all. I will thanks for being for attending to the presentation, and that's all.
Thank you, Nur. Will you be on Discord to answer questions?
Yes, I have to log in actually. Okay. I will log in right now.
Okay, perfect. So thank you. And we are now taking a break for 1 hour and 20 minutes. We'll be back in at 2 o'clock Italian time with 2 talks from Niccolò Valigi and from Jens Weller. Please check the link here for the next session, and see you later. Thank you.